So welcome to everybody. My name is Tobias Goldman and I'm the regional leader of the Stuttgart group of AES Germany. And it's my great pleasure to welcome you all to this event. Today, Dan Dugan will speak about the topic of gain sharing and automatic microphone mixing. If you are interested in the section, our work, or being notified about upcoming online or local events, then please see the QR codes on the screen. They will guide you to our newsletter, the website, and further information about the AES. As I already mentioned, this event is organized by the Germany section of the Audio Engineering Society, and on behalf of the entire team, I would like to thank you for your participation. At the same time, I also would like to take this opportunity to inform you about the upcoming election of AES Germany. We look forward to welcoming a new board and supporting them in bringing in new ideas and continuing what we have already started. The close for the nominations will be this Friday. So if you are interested in being a member of the new board, please send us an email to info@aesgermany.org. Everybody is welcome. Before we continue, a little bit of the household. The colloquium will be held in English. It is divided into two parts. The first part is a recorded presentation in form of a webinar session. And the second part will be an unrecorded Q&A and discussion. In between the two sessions, we have to switch the meeting room. You will find a link to the Q&A session in the chat and on the event page at aesgermany.org. Please make sure that you save it. And if you have any questions during the presentation, there is a Q&A option and a chat option. Please write them there and we will bring them up later. So, without further ado, I would like to hand over to Mariam to introduce our speaker. Thank you.
Thank you, Tobias. It's very nice to see you all here. And this is my pleasure to introduce our today's speaker, Dan Dugan. So let's know Dan a little bit closer before starting the presentation. When Dan was a child, his parents took him to theater and concerts. He always wanted to go backstage to see the light world, not the sound worlds. In his teens, he built a huge model circus and 2 small pipe organs. He was very active in music, singing bass in choruses, madrigal groups, and his church choir. Dan studied math and physics in college, but dropped out to work full-time in the theater doing lighting. That became his first career. At the age of 24, Dan specialized in theater sound, working at the Old Globe in San Diego and ACT in San Francisco. The title sound designer was created in 1968 to describe what Dan Dugan does. He also provided sound services for 8 seasons of the Mandavi Jazz Festival and engineered several independent record albums. Dan demonstrated the first effective automixer at the New York AES convention in 1974. Today, his invention is commonly used but not heard in conferences, in talk shows, in news panels, sports panels, and election debates. The Cinema Audio Society gave Dan the 2018 Outstanding Product Award. He received an Engineering Emmy in 2020. In addition to that, Dan does scientific research in the national parks, making longitudinal studies of landscape, of soundscapes over time. He works in his laboratory in San Francisco, manufacturing his inventions and editing his immersive soundscape recordings. And I think today you are in your laboratory too, Dan, as you mentioned at the beginning. So welcome and thanks for joining us today.
Thank you, Miriam. Okay. I'm honored to be asked to speak by the German section, and I wish I could see a larger audience than the esteemed panel that are here. But we just have to imagine that there are all these people out there, and I'm sure I would love to see you. I'm going to open up my presentation now. All right, we have begun. We've had a number of steps here, and I think I have some slides asking for questions in between each section, but put your questions in the it's the Q&A, is that correct, hosts? That Q&A is where the questions go, and we will see about a question session at the end on a separate channel. Okay, so I'm going to start with some important concepts. The concepts of gain and level. These in common speech are often confused. When we move a fader, we say we're changing the level of the signal, which is our intention. But actually what we do when we move a fader is we change the gain in the signal channel. And when you're going to talk about automatic microphone mixing, it's necessary to make a clear distinction between gain and level, because these two quantities are what determines the automatic mixing. So gain is the amount of amplification of the signal. And that is constant. When I'm not speaking, there is still the same amount of gain in my channel. So it's the amount of amplification. And that, of course, changes when it's adjusted by moving the fader or whatever. Now, the level, that is an ephemeral thing which changes from moment to moment. That's how big the audio signal is. And that changes from moment to moment. And in order to get the level we want, we change the gain of the audio channel. But you'll see how these two concepts interact in the automatic mixers. Now, here's a little more about that, and a little historical note. You may notice some old-fashioned graphics here. Actually, I made this in Mac Paint, the first graphics program that everybody could use without having to have a special graphics computer. That was a great revolution in the day, and I used it to make a presentation. If you have two talkers in a sound system, one of them is loud and one of them is quiet, then you would set two different gains on the preamplifiers. There would be a low gain for the loud talker and a high gain for the quiet talker, achieving the same level. Now, but in order to get the same level, you would end up with quite a different quality of sound on each. The person who's a loud talker would have a nice clear signal. The person who's a quiet talker would have much higher noise coming from the room and feedback possibly mixed in. So matching the levels results in different acoustic gains in the system. Now here's another example. Say you have two talkers who are both normal, and you have a microphone which has a high output like a condenser microphone, and the other one has a low output microphone like a dynamic microphone. And so you would match those gains on the preamps, those two different gains, and to get the same level in your program. And in this case, the noise and feedback in the signals would be the same. Possibly on the one that's high gain, you might have a little preamp noise, but substantially the same. So here, different electrical gains result in the same acoustical gain. So now, in a situation where you have multiple microphones in a live production, three kinds of things work against getting quality sound. the ambient noise pickup increases. The more microphones that you open, the more ambient noise from the room that you get. The potential for feedback increases as you turn on more and more microphones. There would be a limit to how many mics you could open before the system would go out of control. And also comb filtering can occur when the voice going into one microphone is going into the next microphone at a lower level and a different distance, and that causes comb filtering effects. Now, in an event where there's no script, that's difficult to control, and the operator ends up bringing the microphones down and just bringing up down part way and bringing up the one who's talking. But of course, that means they have to recognize who's talking, and they don't know who's going to talk next. So you get what we call upcuts, which is where you see a person's lip move, and then their sound comes on. A late bringing up of the sound that happens frequently in a live production, and then you get that terrible situation where the operator brings up the fader when some new person starts to talk, and they don't hear enough sound, so they push it further because what they're doing is turning up the wrong microphone. And so then the system will go into feedback as they try to get that voice to come out of the mix. So this is embarrassing, and it's very difficult to mix unscripted events. Now, this is the law of open microphones, the number of open microphones. Here is the noise or feedback level, and at the gain of one open microphone, we'll call that the reference of 0 dB. And then if you open a second microphone, then you're going to have 3 dB more of noise from the room, or feedback sensitivity the same way. And if you're open 4 microphones, then you're going to have 6 dB more noise or feedback. So that's the NOM law, which governs what happens when you have more than one microphone open in a room. The other thing is comb filtering. Here's an example of a voice into a microphone, and you get a certain frequency response out of that. Now, when you add you mix in a second microphone at a different distance, then you get what's called a comb filter, because certain frequencies will cancel. They will be out of polarity and cause cancellation dips. And so that is the classic comb filter. Now, to keep these effects from happening, the operator is keeping most of the microphones slightly attenuated and trying to raise the one where the person is talking. Of course, this is a very difficult thing to do and doesn't really have anything to do with how good your ears are or engineering skill. It has a lot to do with luck and being able to see what the people on the stage are doing and being able to identify which microphone to bring up when you see somebody's lips moving. A tricky proposition. Okay, so I came up with a system. It actually, my experience was in theater, and I was doing regional productions of the rock musical Hair, and that had 16 microphones picking up areas on the stage, because this was before the age of many wireless microphones. And so there were 16 area mics to pick up dialogue from the stage. And you can imagine how difficult that was to operate, to follow a fast action around on the stage. So I was looking for something that could do that automatically. So after that job, I thought, well, we need to turn the microphones off and on when they're needed. And when we have more than one microphone on, we need to make a number of open microphones adjustment to the master gain so that it doesn't feed back and we don't get too much noise from the stage. So that was my original objective. I ended up doing something which was quite different, but that did actually solve that problem, but in a different way. Now, the first thing that came to mind, of course, in how do you automatically turn mics on when they're needed is what's called a gate. We're all familiar with what's called noise gates, or in the communication industry, that's called voice-operated switch. Here's a chart of the action, time going this way, level going this way, and here's the output of a level detector on the signal channel. When someone speaks, the level comes up. So you set a threshold so that when someone speaks, the microphone turns on. And that's all very well and good. But sometimes loud sounds will happen in the space, which are much louder than the sounds that you're trying to pick up, the quieter parts of speech. And so if you have a bunch of gates, when the band plays or the audience applauds or something, all the microphones could come on and cause it to feedback or whatever. So gates are problematic in a live situation. Actually, the only really reliable place that gates are used is in on drum sets in rock and roll, because the drum is so loud at the microphone compared to everything else that you can get a reliable threshold there. But with something like a vocal mic, gate is usually unsatisfactory. Okay, so the concept of an adaptive threshold gate is essential to automatic mixing. You have a threshold which is monitoring the ambient noise in the room, say. And so when a person talks at the microphone, their voice is louder than the ambient noise is at that point. And so it turns on the microphone. But when there's a loud noise in the room, the ambience is louder than at any given microphone. And so the microphone would stay off. So an adaptive threshold could solve that problem with with multiple microphones on gates. So I prototyped a crude system which had 2 microphones at each microphone position, and one microphone was picking up the speaker, and the other microphone was picking up the ambience in the speaker's area, and that ambience level was used to set an adaptive threshold. So each microphone had a threshold which is bouncing up and down relative to the ambience at that person's microphone. And these yellow bars are, say, the levels that are going in. And so these 2 speakers, even though they're at different levels, are both turning the microphones on because they're both above their thresholds. And the gains would be usually, you would attenuate in a gating type automatic mixer, you would attenuate maybe 15 dB. You wouldn't turn the mics all the way off. And so this mic is attenuated and the other 2 mics are coming on. Now that's nice, but you hear the effect of it. You hear the artifacts of these microphones switching up and down 15 dB in gain. And you have problems with feedback too as more microphones open. But that's a start. But I decided that was not practical. You would have to have special microphones or something like that in order for this to work, because it's hard enough to set up 1 microphone for each talker. Setting up 2 is unthinkable. So that was a start, but it seemed impractical to me. And as a matter of fact, I did not patent that. And later on, when I had patented a much better way, which I will show you, another manufacturer actually patented this system, and it became a product which is still found in some courtrooms and churches and places around the United States anyway. That was our friends at Shure, and this was called the AMS, Automatic Microphone System. And so it did come to some use eventually. Now, at this time, around 1968, there was a studio gate which was very popular. It was the Valley People Keepex. And the Keepex gate was unique in that instead of switching the channel off and on, it had an expander below the threshold down to a certain depth. And and you can see here actually how this knob is set to 2, which is a magic number for what I did with it. So this would greatly soften what happens around the threshold area and make it a much more tolerable kind of artifact to hear the microphone coming on and off. And so I was inspired by that. And here's what happens in a 2-to-1 expander. This is the input level. This is the output level. And when you're below the threshold, as the input increases, the output increases till you get to the lower part of the expander threshold. Then it's a 2-to-1 expansion ratio. And when you get to the upper threshold, which is sort of normally what you would tune as the threshold, then it's linear again at full gain. And normally you're operating in this range. All the program material should be in this range right here. Okay, now in the automatic mixers that I was building at the time, the prototypes, we had the additional complication that the 2 thresholds were moving together in parallel up and down with the ambient noise, which made it a very complex operation. Oops, went the wrong way. Here we go. Okay, so this is what that system would look like. I discovered that it was virtually just as good to have one ambience microphone rather than one for each microphone. So that problem was solved simply with this. The ugliness of the gates was much ameliorated by the having this expansion region. And so here we have exactly the same result that we had back in the 2 microphone version. Oops, let's go this way, right? That's the same result. But what happened in the margins when it's switching off and on around the edges of it sounded much better. So that was the inspiration for the first working automatic microphone mixer. This was a circuit for the level detector. It really made it possible when I discovered a circuit for a logarithmic level detector in Electronics magazine. Making the level detector log meant that it would have the dynamic range which is necessary in a room. You have in say a church, you may go from a 30 dB level at the microphone when nobody is talking to a 70 dB level when someone is talking into the microphone. So that's a huge dynamic shift, and you want the automatic mixer to be able to track that and read that and measure that. So it's absolutely essential to have a logarithmic level detector. And this was a circuit which was an AC logger, so it was kind of like it would squash the AC signal using a Zener diode as the element. I'm sure saturation, plugins for workstations which imitate tape saturation probably are imitating circuits like this. It's full wave, and so you come out in a filter, so you come out with a DC voltage which is representing the level of the audio signal. And then you also need a VCA, and of course in 1968 and 1969 there weren't much of a choice for VCAs. There was a device made by a company called Vactech, which was a cadmium sulfide cell and an LED. Of course, LEDs were brand new at that time. And they were packaged together so that when the LED lit up, it illuminated the the cell, and the cell would drop the resistance of the photoresistor. And that was quite effective and very quiet, and led to, optical compressors, which were very successful at the time, and emulated in digital circuitry now. However, there's a couple of problems. There's a little timing involved in the cadmium sulfide cell. It has a little memory. It doesn't immediately attenuate back again when the light goes off. And even worse, its characteristics shift over time. They age. And that means that devices that I built with this kind of technology in them would go out of calibration after a number of years, and that's terrible. So anyway, that was the way we started out, and that worked. But then the really interesting thing about this, which I did not realize at the time, is that this has a quasi-logarithmic characteristic to the attenuation relative to the control signal. I wasn't seeking that. I definitely wanted a logarithmic level detector because of the dynamic range that was necessary. But I wasn't necessarily looking for a logarithmic attenuator. I didn't realize that that a logarithmic level detector along with a logarithmic attenuator would have a magical interaction. And that's the stroke of good luck that I mentioned in the description of this session. I wasn't looking for this. It just sort of was the way it was, and it turned out it made something very interesting happen later on. So at the same time, in 68, 69, somebody named Ken Patterson made a number of open microphones attenuators simply by passive attenuation system. And that was actually a company called Diversified Concepts made a number of open microphones attenuator. This was used in systems where seat swivel detectors cause the microphones to come off and on in a legislature or something like that. And that was that could be combined, of course, with with a electro-optical system. And so here was a block diagram, very simplified, of the first working automatic microphone mixer, which I demonstrated at the New York Audio Engineering Society convention in 1974. The audio path is red, and you can see it's very clean. There's no processing of the audio path in any way except for a VCA. And then the side chain is level detectors. You have an ambience mic getting a reference signal for the thresholds. So that threshold is distributed among all the input channels and determines when the VCA is turned on. And then there is a separate NOM function that is looking at which channels are turned on. And this would be what would be called an analog computing, which is what this graph is here now. In analog computing, an arbitrary function generator. You would tune this function generator to make the VCA attenuate 3 dB when 2 mics were on, and 6 dB when 4 mics were on, and so on. And this worked. I set up a bunch of mics in a demonstration there on the floor of the AES in New York, and I could go talk to any of the mics, and each mic came up to full gain in the system, and it sounded really neat. And when I switched it out of automatic, it went into feedback immediately. So it was an effective demonstration, and the first time that such a thing had actually been made to work. So there were, I still wasn't satisfied. I wrote a patent for this and patented it, but it never became a product, never by myself or anybody else made this mixer. Because I started experimenting. I said, well, Still, the reference microphone is a problem. You have to set up this microphone somewhere that picks up the ambience in the area of the stage, and that's a bother. It seems to me somehow it should be possible to derive the signal of the ambience from the microphones themselves, because after all the microphones in the system are listening to the ambience. So there should be a way to get the ambience out of the system. And I tried different combinations, like taking the overall mix and feeding that back as the level and things like that. And then I tried what would happen if I summed all the signals before the process and made that the reference. And all of a sudden, something very interesting happened, which I did not expect and didn't understand at first. When someone spoke, their microphone came up to full gain, and the other ones ducked down. And when no one spoke, all the microphones came up to medium gains that added up to the gain of one microphone. And the NOM circuit was not actuating at all. The sum of the gains was always the same. So when one microphone was full and all the others are down, that was a gain of one microphone. And when all the microphones were hovering at a lower gain, that was equivalent to one microphone. And this was by no means designed, it was discovered. And the NOM circuit became not necessary. And this was because, unbeknownst to me actually, I had matched the curve of the level detector to the curve of the VCA. And these two logarithmic curves were operating in concert. And so in order to patent this amazing thing, I had to reverse engineer my prototype to figure out what I did. And this is a result of, this is now a gain sharing automatic mixer. That was the discovery of gain sharing. You can see again, the red is the audio signal, and that's a very simple path. There's only a VCA, so there's no, echo cancellation or all these complicated calculations that are done on it. It can be very simply done in analog. And then you have the side chain in blue, and you get the ratio between the gain of the level of the signal in the channel to the sum of the signal in all the channels. Now, if these things are logarithmic, then that's simply a subtraction. You're simply subtracting those two things. So it was very simple analog computing. This is the meter that shows you what it's doing, and that's the VCA that does it. And there's no NOM circuit, and all just works like a charm. So I figured out what the formula for that was, and patented that, which was the automatic, the gain sharing automatic microphone principle. Now, and here's what it looks like using the same kind of little chart. The yellow is the levels. The greens are the resulting gains. So if nobody's talking, you say you have 3 mics, there's a low level coming into each of the microphones from ambience, and the resulting automatic microphone mix would be medium gains of the 3 microphones, which add up to the gain of 1 microphone. So it sounds like 1 mic is on. Now, when one person is talking, they have a higher level. The other mics still have the ambience, and the gain is brought up to full, and the other channels duck down. Very interesting. And then when another microphone, that microphone comes up, and the other one's duck down. Just what we want. And if 2 people are speaking together, then the 2 will come up to a little less gain, still adding up to 1 microphone. And this is magic. That's just what you want to do. It turns out, though, it certainly was never my intention to do that, but I discovered something that was much better than my intention. So here's the math. The algorithm is amazingly simple, And I can tell you, if I had designed this algorithm, if this formula had come from my mind to the page, I would be a genius. But I must say it fell out of experimenting. It did not. I did not think this up, and it's so amazingly simple. You take the level of the channel pre-processing, and you take the level of the sum of all the channels pre-processing, and that ratio, you make the channel gain. That's all. That's it. That's the algorithm. Couldn't be simpler. Let's look at some examples, some thought experiments here. Okay, so we're showing gains in red and levels in blue because there's a magic point at which the levels get transformed to the gains. So to start out with, in the 4-mic system with nobody talking, you have, say, at the output of the preamp, say you have a millivolt at each microphone coming out from the ambient noise. Okay, so we have 4 millivolts as being the sum of all the microphones. And then you calculate for each channel, you calculate the gain, which is the level in that channel divided by the sum of the levels. And that gives you 0.25. And you take the gain for each of the 4 channels and add them up, and you get 1. So you have 4 microphones at 1/4 gain equals the gain of 1 microphone. So that's the system when nobody is talking. Second part of thought experiment. Say somebody's talking at the first microphone, and say they're putting out 1 volt from the preamp. Okay, plus a millivolt for the ambience. Ambience in the other mics. The sum becomes 1 volt and a tiny bit. Now the talker's channel is this ratio of this to this, which is very close to 1. Each of the other 3 channels, however, have a very small ratio, and that's just like nothing, close to 0. And when you sum these gains together, you still get 1. Amazing. Now, if 2 people were talking, you've got 1 volt out of this mic, 1 volt out of this mic, a millivolt, you end up with 2 volts and a tiny bit. Okay, and for each of the 2 talking channels, its gain is calculated as 1/2, very close to 1/2. And each of the other channels, again, is pushed way down. And the sum of the gains is 1/2 plus a 1/2 plus a tiny bit plus a tiny bit equals 1. And there you go. So in summary, under each of these situations, you have a gain of 1. And that's just very useful. And notice that this has no threshold anymore. It's just a ratio. There's no gating. It's totally a linear process. So there are no gating artifacts because there's no gating. You're doing very large level shifts, but the level shifts are complementary between the channels. And so all things being equal, they're not audible. So next we should demonstrate this. And to do this, I'm going to share screen here. Well, actually, I'm going to go to a different application. Okay, there we go. Okay, so here we have the remote control panel of a Dugan automatic mixer. And ordinarily on bar graphs like this, you're looking at levels. But in this case, what you're looking at is gains. Now I can show you levels. Okay, here's the levels of the 4 microphones. So that's my microphone is number 3. And Dan, say hello.
Hi, good morning, everybody.
Okay, so that's the levels of the microphones. Now, we're going to go from the levels of the microphone, that's the outputs, and we're going to go to the gains. This is what the automatic mixer is doing. So think of these green bar graphs as faders. The faders are all the way up at unity gain, and when I'm talking. and the other channels are being suppressed. And when I don't talk, all the gains come up to medium gains that sum to the gain of one open microphone. And if you listen to the ambient noise, it's not changing, okay? Even though there's drastic changes happening in the gains of the individual microphones, all the shifts are complementary, and there's no threshold. There's no threshold. There's no threshold. There's no gating. Okay. Now you might think I'm just kidding you with a bunch of LEDs here. So let me bypass this. Okay, that's what you would hear with all four microphones on. And then if we go back to automatic microphone mixing, the ambient level drops by 6 dB, which is the NOM for 4 open microphones. And of course, this is even useful with 2 microphones. And it becomes really essential if you have a whole bunch of microphones. You just can't live without it. Dan, is there anything else in the demonstration that I've missed? You do the demonstration.
I haven't done one in a while, but I think you've actually hit all the main points. When you go into the bypass mode, we can see the utility of this in a multi-mic situation.
Yeah.
How much the signal to noise is improved by using the automatic mixer, and it's really, once you get to that point, I think you've said it.
Okay, thank you. So very good. I think let us go back to this. Okay. Well, the benefits of this function, which by the way anyone can do because the patent is long expired. It preserves the operator's judgment of mix balance. It's not doing the mix at all. It's just doing the cueing in of the mix. It's cueing on the mics that are talking and taking down the others, but it's not really mixing. The mixing part is in the operator's hand on the faders, but it totally eliminates missed cues and upcuts, which is just wonderful. It reduces the studio noise to 1 microphone level. It maintains constant room tone without gating artifacts, and it reduces comb filtering from adjacent mics by a 2-to-1 factor in dB, and it controls feedback by regulating the acoustic gain to 1 microphone at all times. And what can you use it for? Well, gosh, everywhere, anywhere where you've got lots of microphones and it's not scripted. You know, theater shows are operated by these highly skilled operators, and they do what's called line mixing, where they bring up a combination of mics for every line in the show manually. A very highly skilled operation. This kind of mixing, gain sharing automatic mixing, does really syllable mixing, because speech is really a bunch of little tone bursts, and it gets mixed not by the line, not by the word, but by the syllable, by the automatic mixer. So really anything that has multiple microphones that's not scripted can benefit from gain sharing automatic mixing. Here's a favorite example. This was a popular daytime talk show in the US, a huge audience. And on this particular special, there were 32 open microphones on stage. She had 32 audience members on stage, all with lavalier microphones. And here are the operators standing by at the 32 open microphones on this SSL console. And it's all going into an automatic mixer. And basically, they don't need to try and figure out who's talking and bring them up. What they're watching for is trouble. You know, when someone scratches themselves or somebody moves their, makes noise on their microphone, they're troubleshooting. And then when someone is speaking, they can they can tell from the automatic mixer, they can see who's talking. And they can grab the fader and mix appropriately, artistically, the person who's talking. So there's 32 open microphones helping these two operators on something that otherwise would be virtually impossible to do. And so I think we should probably go to questions now, and then I got more slides that I could show if we have more time. But how are we doing on time?
It's about 10 till we're 50 minutes in.
Good. Okay. Well, that's quite good. Let's see what's next. Let me just cover this. This ad was in. It says at the top where that is. Yes, it's 1961. That something like that happened in automatic mixers too, because when there was a first round of automatic mixers that, since I had patented the magical way to do automatic mixing, people came up with all sorts of different ways, and some of them sort of worked, and some of them were awful. But it became a product category in sound reinforcement. And then later on, when the patent expired, people could do gain sharing, which they do now, and they could do their own versions. And quite surprisingly, these versions are all different a little bit. I'm not sure why that is, but people, engineers never want to imitate something. They want to make it, put their mark on it. And I call them honorable imitations. Because they're interpretations of the expired patent. And they're all a little different. They often add parameters to it, which in my opinion is a mistake, because the parameters can be optimized for speech and you shouldn't mess with them. You shouldn't have control of shouldn't be changing the attack time and the decay time of the level detector. A generic description was invented for it called gain sharing. And they shouldn't mention my name because that is a trademark. Now, I still sell automatic mixing controllers, which are black boxes, which put the function into your console. And this is sort of modeled after Dolby. It's a process which, no matter who manufactures it, it performs identically. And the parameters are optimized. You don't adjust the algorithm, and is a standard of quality. So if you have a Dugan licensed automatic mixer, you know exactly what it does, and it does exactly what you want, I hope. And there's lots of consoles available with automatic mixing in them, gain sharing, and these are the ones which are actually licensed from me. Let me just mention one more thing. Some people say that, well, this is going to make young mixers lazy. It's going to make people not learn how to mix. Well, I think that queuing in the mics is not really a humane function. Queuing in mics is something that's very welcome to let robots take over, because it's not the art of mixing. The art of mixing is making things sound good, equalizing different voices so they all sound nice, taking out the bumps and low frequency stuff that comes in by accident, balancing people when they lean back from the microphone and need to be raised up, paying attention to the show, being a brain on the job is very important. And that's the art of mixing. It has nothing to do with trying to figure out who's talking in a panic when you've got 12 doctors on the stage 200 feet away from you. That's not the art of mixing. So anyway, happy. And let's go to the Q&A period.